Hello, I am Michael Selwanis, a PhD student at the Mechanical Engineering Department, Polytechnique Montreal. I'm working with Professor Guilherme Franzini, Polytechnique University of Sao Paulo, Professor Cedric Béguin, and Professor Frédéric Gosselin, Polytechnique Montreal. This short video outlines our article entitled Multiple Balls Rotating in a Circular Track Experimentally Mitigate the Galloping of a Square Prism.
In this research, we propose a rotative nonlinear energy sink composed of multiple poles free to rotate in a circular track. Such a simple device absorbs the energy of a vibrating structure through the motion of the pole and the collisions between them. Transverse galloping is a type of flow-induced vibration. During heavy wind, it can lead to catastrophic effect on many structures, such as power lines, sign supporting structures, and high-rising buildings. The proposed multi-pole nest is used to mitigate the galloping of a square prism in wind tunnel experiments. We designed a simple structured device that can be easily mounted at the top of a square prism model. The prism vibrates transversely to the flow, resulting in automatic rotation of the nest balls. The balls rotate in a circular track of mean radius r, affected by the damping force due to the friction between the balls and the nest track. We perform all the experiment in the closed-loop wind tunnel of Polytechnique Montreal. A lightweight square prism model is elastically mounted inside the test section by two identical supports above and below the test section. The nest is mounted at the top of the square prism model outside the test section. Hence, the flow has no direct effect on the ball dynamics. The proposed nest is composed of main body, bushings, and metal balls. By swapping some parts, we obtain various configurations of multi-ball nests of equivalent mass and mean track radius. Through wind tunnel experiments, we measure the galloping amplitude of the prism with the different configurations of multi-balls to demonstrate the ball number effect on the nest behavior. Two pairs of end and inner plates are attached to the model to prevent airstream escaping the test section and help assume two-dimensional flow conditions. Slots of 15 cm length at the ceiling and the floor of the test section limits the maximum amplitude of the prism. A high-speed camera captures the motion of the vibrating prism and the rotating balls to allow for post-treatment image analysis. The mass distribution of the balls and the collision between them significantly affect the multi-ball nest behavior. Depending on the arc angle that we defined as the angle between tangents of a ball passing by the nest center, we highlighted two important parameters for the design of the multi-ball nest, which are the track crowdedness ratio and the maximum radius of the nest mass center. The crowdedness ratio indicates the part of the track filled with balls. Increasing the crowdedness ratio decreases the mean free path of each ball and leads to less effective collisions. Regarding the radius of the nest mass center, decreasing it is favorable within a certain range unless it's too small to sustain the dynamical coupling of the prism with the balls. For generalization, we present our result in the non-dimensional form. We plot the prism amplitude at different reduced velocities. The red horizontal line represents the limit of our experimental setup, which is equal to 1.5 times the square prism side length. The following figure compares the response of the prism without the nest, represented by a continuous curve, and with different configurations of multi-ball nests. Without the nest, the prism amplitude increased dramatically to reach the limit of our experiment at a reduced flow speed close to 15. The multi-ball nest delayed the occurrence of galloping. The experiments provided that increasing number of balls from 1 to 2, 3, and 4 reduces the prism amplitudes. Regarding the nest working range, using two balls increases the flow critical speed at which the prism amplitude reaches the limit of our experiment by 9% compared to the one ball. This speed remains constant for the 3 and 4 balls. Any further increase for the balls number above 4 slightly reduces the galloping amplitudes, but it limits the working range of the nests using 5, 8 and 10 balls. For the one ball nest, the oscillatory regime appears at low flow-reduced velocities, in which the small oscillation of the ball are sufficient to absorb the prism vibration. Increasing flow speed changes the response of a single ball from the oscillatory to the rotational response. In the rotational regime, the ball continuously rotates with the same frequency of the prism to kill the galloping amplitudes, and then it stops until the galloping amplitudes grows again to a threshold value. This cycle is repeated periodically, resulting in a strongly modulated response of the prism. For balls, dynamics are different. At low flow speeds, we observe a weak response in which the ball oscillates with small amplitudes all close together. High flow speeds represent a higher excitation level for the nest and lead to a strong response mode, at which the balls move around, varying the space between them and leading to a wide range of fluctuation for the nest mass center radial location. The wind-rose graph was sufficient to present the different responses of the multiple nests in our article. At a reduced flow speed of 17.4, the weak response characterized by small oscillation is reflected by one color, which indicates the small fluctuation range of the nest mass center radial location. While at higher reduced velocity of 24.8, the strong response is reflected in many colors, indicating a wide fluctuation range for the nest mass center radial location. To sum up, multi-ball nest is more effective in reducing the galloping amplitudes of a square prism compared to the single ball nest. Increasing the number of balls expands the nest effective range. The 4-ball nest increases the reduced velocity of large amplitude galloping by 9% compared to the single ball nest of equivalent mass. Too many balls overcrowd the nest track and decrease the nest working range. We acknowledge the Moretti Technical College in Egypt and the Natural Science and Engineering Research Council of Canada for sponsoring our research. Thank you for watching the video.